All right, we are moving into section 2.2 where we're looking at the kind of an informal or preliminary definition of a limit. We will get to the formal definition of a limit later in chapter 2. But we saw in section 2.1 the idea of a limit numerically. So we were looking at different values that were very, very, very close to the value that was in question. Now we have the opportunity to look at limits graphically and with tables again. So here's a preliminary definition of our limit. So, all right, we're going to suppose that the function f is defined for all x near a except possibly at a itself. And if f of x is arbitrarily close to some limit L, we'll call it, as close as L as we would like to be, for all x sufficiently close to but not equal to a, then we will write that the limit as x goes to a of our function f of x is equal to L. And so the way that we say that is that the limit of f of x as x approaches a equals L. Or sometimes I'll say the limit as x approaches a of f of x equals L. So make sure you get every piece in there whenever we're working with that. Now, there are many times when the limit is equal to our function value at a. But there are other times when the limit L and f of a will differ in the value, and sometimes we'll see where our function value at that a may not even be defined, and that's all okay. This is kind of getting us prepped into when we get into section later in chapter 2 on continuity. I believe it's 2.6. Okay? So we're first going to just kind of look at some graphs and determine some function values and some limits. So remember, a function value is exactly where that function is. Notice by a solid dot. Notice by all of these are where our function values are connected with that solid line. So if I ask you from this graph, what is f of 1? F of 1, I go over to x equaling 1, go up to where I find the function or I find a dot. So in this case, the function value is right here, and f of 1 is equal to 2. Now, if we look left or right of x equaling 1 on our function, what is the limit of this function at that point? So again, we're going to get very, very close to our x value, but possibly not equal to that. And in this case, as I come from the left of 1 and from the right of 1, I'm honing in right here at that value of 2. So this is a case where our function value and our limit values are equal. Now, let's turn to x equaling 2. If I ask you what is f of 2, what is the function value when x equals 2? Again, I'm going to come up here, but look, there's this open circle here, which means that that's not where it's equal to, and I come up to this solid dot. Therefore, f of 2 has to equal 5. Now, if I look for our limit as x goes to 2 of f of x, then again I'm looking at where the function is getting closer and closer to 2 from the left and closer to 2 from the right, and notice we are honing in at the same area. When we're on that function getting closer and closer to a, that value is equal to 3. So this is a classic case where the function value does not equal the limit value. There's a jump here within there. All right, let's try f of 3 and the limit as we approach 3. We go over to x equaling 3. I go up and I figure out where that solid dot is or where I'm passing through on the solid line. Notice there is nothing. So this is a case where my function value does not exist. And so does it mean that automatically my limit doesn't exist? Because the function value is defined around x equaling 3. So as I come from the left of 3, I get closer and closer here. From the right of 3, I get closer and closer here. Therefore, my limit is equal to 4 in this case. So what I have previously, we have in this example one of each one of those cases where the limit equals the function value, where the limit and function value are different, and where the function value isn't even defined. Okay, so let's change our graph and let's try these limits. Okay, so using the function or the graph of f to determine the following values if possible. So if I want to know what is f of 2, where's that solid dot or where is it coming on that function? Bam, there's a solid dot. So this is equal to 2. What do I know about the limit as I'm approaching 2? So from the left of 2 and to the right of 2, what happens to my function? I come up here. On left of 2, I'm honing in on 4. From the right of 2, as I get closer and closer to 2, I'm honing in on the y value of 4. Therefore, that's what my limit is equal to. Let's move along to x equaling 4. So I come over here to x equaling 4. I'm looking at the limit. So again, kind of go on that function. From the left, I'm honing in here. From the right, we're honing in here. What is that y value? That y value is 4 as well. And lastly, when we find x equaling 5, I come up here. Here's where the value is. Now that f of 5, the function value is equal to 2. And as I come from the left of x equaling 5 and from the right of x equaling 5, I hone in right here. Therefore, my limit is equal to 2. So make sure that you're looking left and right for the limit to exist. We will see in some cases where that does not occur. Okay? Now, finding limits with tables, and we're going to look at a table situation to see if we can determine the limit. So this is kind of similar to what was done in the previous section 2.1 when you're looking at a bunch of decimal values. So you may want to have your calculator handy for this because they are not the prettiest of all. Create a table of values of f of x equaling the square root of x minus 1 all over x minus 1 that corresponds to the value of x near 1. Then make a conjecture or a guess, an educated guess about what is the value of that limit as we approach 1. So here we're coming from the left of 1, here we're coming from the right of 1, and we want to know kind of what is that limit if we are not necessarily equal to 1, but very, very, very close to 1. So that means I need to take this x value and I need to plug it into this function in 2 places, so here and here. So again, you can use your calculator to do this. I'm going to go ahead and when you put it in a scientific calculator, make sure if you do it all at once that you do like the square root of 0.9 minus 1. Make use of parentheses because if not, then it's going to kind of do the order of operations out of the order that we want it to go. Okay, those scientific calculators have their own mind. So make sure you force it to do the subtraction on top, subtraction on bottom, then divide the 2. So here are the values that you get whenever we are coming from the left of 1. For 0.9, that function gives me 0.513167, let's say. Okay, so close to a half. This one, if we put 0.99 in for each of the x values, I get 0.501256. Okay, that's a little bit smaller, closer to 0.5. That might be kind of setting in our head here. Putting 0.999 in gives me 0.500125. Again, getting closer and closer to a half. And on this one, it's 0.500013. And so, coming in from the left, I might choose a guess as to be 1/2 or 0.5. So let's see what happens when we come from the right. So let's start here at 1.1. Putting 1.1 in there, underneath that square root and in for the x, the value you get is 0.488089, let's say. And you can round those off a little bit. I like to go a few decimal places out. Putting 1.01 in, we get 0.498756. Getting closer to that 0.5 is what we thought the guess would be. 1.001 yields a 0.499875 decimal, 0.499875. And putting in this one that is the closest that we're putting into 1, we get 0.499988. And so, if I were to make a conjecture, to make it kind of a guess, I would definitely choose 0.5 as my conjecture, because coming in here it's close to 0.5, coming in the other direction is close to 0.5, and so therefore you could say that, or you could also say 1/2 if you so choose. Either way it works. Okay? Alright, very good. So you've done that in section 2.1. We may do a little bit more of that to get that idea across. So, we can talk about one-sided limits. What we were looking at is kind of from both sides. So if I have the limit as x approaches a of f of x equaling L, that is referred to as a two-sided limit because f of x approaches L as x approaches a for all values of x less than a and values of x that are greater than a. Okay, so it kind of gets both sides there. Now, for some functions, it makes sense to examine the one-sided limit, which we end up calling the right-sided limit or the left-sided limit. So the function I'm thinking up off the top of my head is the square root of x function, which if you recall does something like that. It would make sense to come into 0 from the right, but it does not make sense to come in for 0 from the left because it's undefined in that area, okay? So let's formally define these left and right-sided limits, starting with the right-sided. Suppose that f is defined for all x near a, with x being greater than a. So we're to the right, we're bigger than a. Now, if f of x is arbitrarily close to our limit L, for all x sufficiently close to a, with x greater than a, again with values that are bigger than a, then we write the limit as x approaches a with a superscript of a plus there. That's what makes it a little bit different. And that symbolizes that we're coming from the right, on the positive side of a. And we say that the limit of f of x as x approaches a from the right equals L. Okay, just some terminology there. Now, similarly, on the left-sided limit, we're going to change this inequality, but we're also going to change that superscript. So suppose that f of x is defined for all x near a, with x now being less than a. So the x that's in question, the 1.1 or the 0.9 and the 0.99, has to be less than the a value. Now, if f of x is arbitrarily close to our limit L, for all x that are sufficiently close, very, very, very close to a, where x is less than a again, then we write the limit as x approaches a from the left. So this time we use a negative, symbolizing that we are to the left of a of f of x equals L. And again, we say that the limit of f of x as x approaches a from the left equals L. Okay, so you just have to go on one side. If there's not a plus or a minus there, that means that we're going from both sides. So you have to check both. Even though it doesn't say it, sometimes you do have to check both when you're on those two-sided limits. But for one-sided limit, we're just going in one direction. All right, let's try this one. According to the following graph, find the following limit. So the limit here is g of x over here. We have kind of a jump in here. If I ask you for f of 1, I hope you would tell me that it does not exist. There's not a solid line there, or a solid point there. And so, as we approach x equaling 1, this time we're going to go with a plus there, so that means from the right. As we are on our function and we're approaching x equaling 1 on the function from the right, so to the right of x equaling 1, follow that function down. Where does this hone in on? The y value that it hones in on is -2. Therefore, this right-sided limit would equal -2. If I then am asked to look at what is the limit as x approaches 1 from the left, so on the left of x equaling 1, I'm going to follow that function down to where it is honing in on. As we get very, very close to 1, that y value is equal to 2. So notice here, we have a case where the right and the left side of the limit are not equal, and that's okay. Sometimes those things happen. Now, let's look at this graph. This graph is the square root function, but we've shifted it to the right by 2. Remember, this gives me, you're going to the right by 2 and up by 3. So to the right by 2 and up 3, that gives me that new point. And if you recall, for the square root, our key values from that starting point were 0, 0, 1, 1, and 4, 2. So that means from here I'm going to go over 1 and up 1, over 4, 1, 2, 3, 4, up 2 gets me about there, and that gives me my function. Okay, so if you like to see it with that graph, go ahead and graph it. Let's answer the question about this limit as we are honing in on 2 from the right. So here's x equaling 2. I'm going to follow my function as it is coming in from the right, and where does it get very, very close to? Gets very, very close to this value here, which is 3. On the other hand, whenever I look at honing in from x equaling 2 on the left-hand side, notice there is nothing on my function on the left-hand side. It is not in the domain. Nothing exists here, so we can't even answer this problem. We basically just have to say that that limit does not exist. And if the reason, you're asked the reason why is because those values are not in the domain. Okay? All right, very good. Moving right along here. So now that we built to the relationship between one-sided limits and two-sided limits, this is important in whether or not the limit exists. So back here on this last example, not the last example per se, but the second to the last example, here we had two limits that came into different values. And so we have to assess, in order for us to give a two-sided limit, whether or not those left and right limits are equal. So this is kind of where we bring it all together. So we're going to assume that f is a function that is defined for all x that is near a, except for possibly at a itself, because back on that g function, there was nothing equal to at that x equaling 2. Then the limit as x goes to a of f of x equals L. No superscript here, so that means that that's the two-sided limit from both sides. That is equal to L if and only if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the left of f of x, and both of those have to equal L. Now, it's a possibility that two of those things, they may end up having a different value, but for this to occur, it has to be the exact same value. Therefore, for a limit to exist, the limit from the right must equal the limit from the left. And if so, then that is the ultimate limit that we have for that function. Okay? So, for the g function on the previous page, let me remind you what that looks like right there. Does the limit as x going to 1 of g of x exist? Well, we have to assess the limit from the right and the limit from the left, and we look at these two values. Notice that those limits are different. Therefore, the answer to this question says, does that exist? The answer is no. Why? Because the limit as, limit as x approaches that one value from the right of g of x does not equal the limit as x approaches 1 from the left of g of x. Okay, one is -2 and the other is 2. All right, very good. Let's kind of hone in on multiple examples here. Not that it's hard, it's just a lot of these examples kind of hone in on that, and they're really short examples, so we can kind of work through these. So we're going to use the graph at the right of f in this figure to find the following values or state that they do not exist. So if it does not exist, explain why. We're just going to do that verbally because I don't have enough room here to put that in there. All right, so let's look at f of 1. Again, go on the x value. X equals 1. Where does it equal to? A solid dot or a solid line? Bam, right there. It is equal to the y value that matches of that, which is 3. Going across, what's the limit as I approach 1 from the left? So I come up here and I hone in from 1 from the left. That looks like it comes in at 2. And the one from the right, following my function as I get very, very close to x equaling 1, and the y value of that is also 2. Notice that those are both the same. So in part D, when we say what's the limit as x approaches 1, they are exactly the same. That limit exists, and that limit exists at 2. Okay? Let's move on to x equaling 3. X equaling 3, the function value is at the y value of 2. And I'm going to hone in on my function as we approach 3 from the left. So here's 3 from the left. Go out to the side here, and we're approaching 3 from the left. That has a matching y value of 4. If I then go to the right in part G of 3, so I'm going to come up here on this part of the function, and I'm coming to the right of 3. Notice that that value is at y equaling 1. So if I put those two things together for the two-sided limit as x approaches 3, we have to assess, does this equal this? And in this case, it does not. Therefore, the limit on the two-sided part as we approach 3 does not exist. And the reason is because the limit from the left does not equal the limit from the right. All right, very good. Let's look at f of 2. F of 2 coming up here. Now it's not an exact point. It is, but it follows through on this solid line. We have a y value of 3. If I look at 2 from the left, notice comes into 3. 2 from the right comes in at 3. So the next two answers are 3 and 3. And we assess those two answers to answer the last question of the two-sided limit as x approaches 2. That means that we end up having that value of 3 as well, making it exist at that point. Okay? All right, very good. Now, we're going to move into a graph that we're going to have to sketch, actually a couple of them, and then we're going to be able to take some information and graph something ourselves. So here, I like to have this rational function, which includes this absolute value, because it actually will turn into a piecewise function. If you recall, absolute value of x was defined to be x and negative x if x is greater than or equal to 0, and if x was less than 0. So we got to split it up as to the exact thing or its opposite. So here, the absolute value of this, its breakpoint, if I were to graph that, that's a right shift of 3, and it would look something like this. So that means that breakpoint needs to be at x equaling 3 versus this x equaling 0 at that point. All right, so now we are going to kind of change it into a piecewise function first and then graph it, okay? So I need to first, notice this is a trinomial that I might possibly be able to factor on top. So if I'm able to factor that, I need two binomials. I need an x and an x. The last sign is a minus, so they are different inside, plus and a minus. And what do we multiply to get 6 that we subtract to get 1? Well, the two factors of 6 that I need are 3 and 2. And so that ends up, I need a minus 1 there, so I need a negative 3 plus 2. Again, make sure that you are sufficient or efficient with factoring. Now, if I'm going to break this now for x greater than or equal to 3. So that's my break point here. So what value do I need? Do I need x minus 3 or the opposite of that for all values that are greater than 3? Well, think about it. If I put 4 in there, 4 minus 3 is 1. The absolute value of that is the same thing. So when x is greater than 3, that function, the absolute value, can just come down to x minus 3. Okay, which is nice, because notice here, this ends up canceling. All right, so I'm going to factor, same factors on top, but whenever I now turn to the restriction where if x is less than 3, that means that if I throw like 1 in there, 1 minus 3 is negative 2. The absolute value of that I have to take the opposite of. So that means that when I take away the absolute value and break it apart, I have to do the negative on this term down here where x is less than 3. So when I do that, these again will cancel out. So what I finally have for my g of x function that I'm going to choose to graph with is, I'm left with an x plus 2 if x is greater than or equal to 3. And I have this negative down here that I could kind of bring up front and distribute if I want. So as a negative x minus 2 if x is less than 3. And let's see if we can graph that, okay? So, a couple ways you can do it. If you want to start at x equaling 3 and throw that value in, I'm going to be at 3, 5. At x equaling 4, notice I did a solid dot because I chose to do the equals there. If I put 4 in there, 4 plus 2 gives me a 6, so I would be here as well. And that line is just going to do, with our intercept, it had a plus 2 intercept, up 1 over 1, up 1 over 1, up 1 over 1, but we don't start until x equaling 3 because that's where we're restricted with. So I would have a line that looks like that, kind of off the grid a little bit, that's okay. Then here, again, if you want to choose for x equaling 3, now we're not going to put a solid dot there, but if I put 3 in here, negative 3 minus 2 is a negative 5. So at 3, we're at negative 5. I'm going to open circle that. What happens when x equals 2? 2 in there. Negative 2 minus 2 is a negative 4. So I have this point. Or you could use your slope to get your next point. With a negative 1 over 1, means I can go down 1 to the right 1, or I could go up 1 to the left 1. So I would end up having these points here, and I can draw that graph as well. Okay, so there's the graph. And now that we have that, we have to determine what are these limit values for a, b, and c. around the cutting point or that break point of 3, what happens whenever on my g of x function as I approach 3 from the right? So to the right, I'm up here on this line, and I'm honing in on this value, which is y equaling 5. When I go from the left of 3, I'm on this line right here, and I'm honing in down right here, getting closer and closer. That y value is negative 5. And now in order to look at the two-sided limit in part C, I would have to assess, does the limit from the right equal the limit from the left? In this case, it does not. Therefore, this limit does not exist. Okay, there's a jump in the graph there. That would constitute the limit not existing. Okay? All right, very good. Last one that we have to graph, and then we're going to create a graph on our own and be done. So we are going to sketch this square root function, this constant function of 0, and this line of 1/2 x plus 1. Our breakpoint here is at x equaling 2. I'm going to go ahead and do this middle one first because there's not really a range. It's just at x equaling 2, I get 0. So x equaling 2, my y value is 0. That's my point. This is the square root function, which we saw that on the back side of the page. Remember, this plus 2 inside here tells me that I would move it to the left by 2. So I'm going to move it to the left by 2. That's going to be kind of that turnaround point. But notice, I don't need all of that. I'm looking at a piecewise here, right? Because really, technically, I'm for that piece. Oh, I do need that part. Sorry. For that piece, I want to be less than 2. So I want everything less than 2 on that square root graph. So the t-table that we had for that was over 1, up 1, over 4, 1, 2, 3, 4, and up 2. Now, since we're equal here, we are not equal here. So I'm going to open that circle, and that would give me that graph right there. Okay, so that's just the square root of x plus 2. Now, it does honestly keep going on and on and on, but remember we cut it off there at x equaling 2. Now, when x is greater than 2, I am on this line. Now, you can, if you want, plug 2 in. That's not too bad. 1/2 of 2 plus 1. That would give me a 1 plus 1, which is 2. So for our line at 2, now I'm still going to have an open circle because I do not have equals, but I would be at this point on the line, and with my slope I can actually now find another point. The slope is 1/2, so I can go up 1 and over 2. I can go up 1 again and over 2, which would be about there, and I can construct that line to go off into infinity. So this is the graph that we have in this situation, a piecewise function, and now we have 4 things that we need to find. What is f of 2? I'm going along here. Where's the solid version at x equaling 2? It is on that point at 0. And what happens when I look at that limit from the right of 2? From the right of 2 means I'm on this function. Where am I coming into? I'm closer and closer and closer to this y value of 2. And if I come from the negative direction of x equaling 2, I'm along that square root function. As I get closer and closer and closer there, then I hone in around that value of 2. And to find the two-sided limit without a plus or minus on there, we have to assess the limit from the right and the limit from the left. Notice that they are equal. Therefore, our limit two-sided is going to be 2 as well. Okay? All right, very good. Last problem on this section. Then we'll move in to how to compute limits analytically, mathematically, okay, without graphs and tables. That'll be the next section. So we are going to now take some information and create a graph. Now, there could be multiple answers to this type of question, just where you can get a sketch on a graph that symbolizes everything that they've given you. So I always like to start right here, okay? These are those function values, those dots that I have for inside my graph, so that we have each one of those working. Okay, so f of 1 would be here, where it's at 1, 0. Then we have the point 2, 4 would be this one. And we have the point 3, 6. I'm going to go over 3 and up to 6, which would give me this point as well. Now, we also have to work with some limits. And notice these are a one-sided limit around x equaling 2, which means that I'm honing in at -3 as 2 comes from the left. So kind of think about 2, -3. Now, that's definitely not where it is equal to, so that means I'm probably going to have an open circle. If I hone in from 2 from the left, that means I have to hone in down here at that -3, okay? So anything, the function that's coming from the left means that I've got to kind of come down and hone in as I get closer and closer to x equaling 2. The y value has to get closer and closer to -3. So here you have the choice of, if you want to do a straight line that goes up like that, you could do a parabola that goes up and down. You could do another little squiggle. It's all up to you. I just kind of like to sometimes do the most basic, where I have a linear equation. So that takes care of this. And it takes care of this, okay, fully. Then, if I look at my last limit, as I hone in around 2 from the right, that means I have to hone in around y equaling 5. So 2 from the right, I have to come in here around y equaling 5. So that means here is the x value of 2 and the y value of 4. That's the function value there. But this is where my function has to appear off here, to where I have to limit to 5. So again, you could do a linear case where you're coming in to the right of 2 and going down to y equaling 5. Or you could go through that value and do kind of a parabola or something like that, to where that will work for the function. You're honing in at 5 as you get closer and closer to 2. So this one works. I went through the point at 3, 6, and I kept my point at 2, 4. And so those would all be satisfied. Again, there are multiple graphs that you could have. Infinite, actually, number of graphs that you could put on a situation like this. Okay? All right, so the main thing on this is kind of our first preliminary definition of a limit. Also talking about two-sided limits coming in from both directions. And in some cases, looking at one-sided limits where you're coming from the right or coming from the left. So again, next section we'll be looking at how do we mathematically find a limit analytically. All right, so until next time.